I prepared this review, essentially all the stuff which will be covered on the exam. So first we introduced capacitance, you remember, then applied that to find capacitance of a parallel plate capacitor. Then this was covered in your labs, in your lab class. Again, as I said, this material might be among multiple choice questions, right? Opens easy conceptual questions. So then after that, we move into current-related quantities. We introduce the current, Ohm's law, introduce the resistance, then introduce the resistivity, and wrote down the expression which can be used to find resistance of some typical resistor. Then current density, all right. Then also the method of an equivalent resistance, which can be used to analyze the circuit full of resistors. Again, what does it mean, analyze a circuit full of resistors? You remember that circuit trinity, R, I, delta, V. So if you know resistance, then you just need to find current and the potential currents and potential differences. If you know those three, you know everything about resistor. Okay, so first we use this method to analyze them. And so that's what we need to know. We need to know, of course, the formula, how to find equivalent resistances. And all students who sit here in the class, they know these formulas. The only trouble's over here. So you just need to remember that current through the equivalent resistance equals to the current through resistors connected in series. And again, this is, I started giving this in the formula sheet, so this is given, right? So before, I used to skip this part, just the formula. But then, since I saw students struggle a lot with that, so I decided, okay, so let me give that formula. Then in case of the resistors being connected in parallel, and I didn't label them, R1 and R2. Then the formula which can be used, we need to deal with the reciprocals, and the potential difference across the equivalent resistor equals to the potential differences across the resistors connected in parallel. And then the final piece of material which we discussed, electric power, of course, and Kirchhoff rules, junction rule, the total amount of current entering the junction point must be equal to the total amount of current exiting. In the loop rule, if you take any loop in the circuit, walk around in a certain direction, counting, adding all the potential differences across each element. When you get back to the starting point, you must get 0. Right? Okay, so essentially that's what we need. And now let's start discussing problems. If you have any questions at any moment of this exam review session, just say something, right? So we can discuss that, right? So don't be afraid. Okay, so the first one. Let me just write number 1. And this problem is similar to the conceptual questions which we discussed in the class. And this time I decided to present it as a problem. So it's about capacitor. So let's assume that we have a parallel plate capacitor, PP capacitor. Right. And, okay, you know what, let me draw it quickly. So this is the part A, in part A. So we have a plate, right? Let's say like this. Area is given, 25 square centimeters. Right. Then distance between the plates is also given, let's say D1. Right now I'm using subscript D1 because for part B the distance will be different. So that's why I put a subscript over there. So D1 equals to 2 millimeters. Right. And the whole thing, the capacitor is connected to a battery, 12-volt battery. Okay. Delta V. So the potential difference is 12 volts. Okay, so that's the situation. And part A, the first part, part A, it's quite straightforward. So essentially, we want to analyze this capacitor. So we need to find capacitance, discuss potential difference, and find a charge in the capacitor. Right? So just straightforward things. And so first, I want to again discuss what can you say about the potential difference. And again, you see I put a subscript 1. it's a potential difference across this capacitor in part A, because in part B, it might be different, who knows. So I put subscript 1. So potential difference across the capacitor equals to the potential difference you don't need any notes. You know the answer. I just want to discuss then again quickly physics behind that answer. So what's the potential difference across the capacitor if it is connected directly to the battery? Of course, come on, why are you so hesitating? The answer is trivial, right? Of course. So potential difference across the capacitor equals to the potential difference provided by the battery. Delta V, it's a battery. So the justification, we justified it like maybe 7 classes ago with this. So the justification is this. Look, essentially this circuit consists of just 2 big pieces of metals. That's it, the whole circuit. Look, the first part, the first piece of metal, it's this one, right? And the second part, which is also just a piece of metal, but different, right? It's this one. Nothing else, just 2 pieces of metal. And if we assume that the capacitor is already fully charged, then, of course, there wouldn't be any motion of electrons in this piece of metal and that piece of metal, right? So it means that what can you say about the state of this piece of metal? How do we call that state? You remember? The wire. No, you remember it was somewhere before we started discussing simple circuits, we discussed properties of conductors. You remember? Electrons stop running when conductor reaches electrostatic equilibrium. Electrostatic equilibrium. So essentially in the electrostatic equilibrium, what do we know? Electric field inside of the metal, 0. And what do we know about the electric potential? It's constant everywhere, at every point, right? So pretty much it means that if this electrode of the battery is, let's say, at plus 6 volts, then all these points are going to be, okay, I erased it. All these points, and even here on this electrode of the capacitor, will be at plus 6 volts, right? Because again, this capacitor is fully charged, so current stop running, so it means that now this piece of metal is in the state of electrostatic equilibrium. So this will be at plus 6, and then I can say exactly the same thing about this piece of metal. But now, of course, it will be at minus 6 volts, all these points. So as a result, plus 6 over here, minus 6 over there. Of course, potential difference across the capacitor will be exactly the same as the potential difference across the battery. So if the capacitor is connected to the battery, then every time potential difference is going to be equal to the potential difference of the battery. Okay, so that's just the justification, but most of the students usually, you know the answer. Just very often students cannot justify the fact why delta V equals to the delta V of the battery. Okay, so we discussed delta V. Now let's discuss capacitance. Again, the circuit trinity, we need to discuss 3 parameters. So capacitance. And let me label it as C1. Can we find capacitance? Yes. And you remember what's the major feature of the capacitance, at least for a parallel plate capacitor? It depends only on the geometry, right? Of course, what also important one between the plates, but in this case, every time in this course, we have vacuum between the plates and system in a vacuum, right? So yeah, we just need to know geometry, and geometry is given. Area is given, spacing is given, so we should be able to calculate. But of course, all these parameters must be converted into meters. Okay, so it will be epsilon naught A over D1. And on the exam, if problem consists of several parts and you use, there is a D1, D2, use the subscripts. Never skip subscripts because it's, okay, it's, again, we're not in psychology department or philosophy department. We need to denote everything properly because I notice students very, very kind of sloppy and reluctant to show the subscripts. Right? Develop the strong habit of doing that. So, all right, A, you know what, let me convert area this below. 25 square centimeters, it means that we need to let's say 100 centimeters, it's 1 meter, and we need to apply it twice. Right. So, of course, you can get, so it will be 25 times 10 to the power of minus 4 square meters. And d1, of course, it's easy. 2 times 10 to the power of minus 3. Okay, anyway, so if you apply that, you will get, where is my answer? 11.63 times 10 to the power of minus 12. And units after great guy Farad. Right. Yeah. I read originally farads were used to denote units of charge, and then they decided at the end of 19th century decided to change the game, right? So, and farad now is used to denote units of capacitance, and coulomb units of charge. But anyway, so F capital farads. Okay, so now delta V we found, capacitance we found. Now we need to find the charge. So, and again, I will put a subscript 1 because it's a charge in the capacitor in the part A. In part 1. So Q1, it will be C times delta V, right? So C1 times delta V1, C1 times delta V1. Okay, so we found everything. So if you plug and calculate, you will end up with 1.33 times 10 to the power of minus 10 coulombs. Units of charge, coulomb. Okay, so this is straightforward. Right, so now part B. So now, let's assume that capacitor is still connected. C, C is still connected to our battery. And then we put the rubber gloves on and reduce the spacing by a factor of 2. You remember we had these questions, this similar question as a clicker question. Right? Okay, so now still connected, but we will take D1 and divide it by a factor of 2. So now it will be 1 millimeter essentially. Right? Okay, so now let's analyze the same. So let's discuss potential difference, charge, and capacitance. So let's do the same thing, but now if we change the distance. Okay. Since I bugged you about that question, and now let me continue bugging you. What can you say now about the potential difference across the capacitor in this case? Delta V2. Yeah, it will be still 12 because again, I can give you exactly the same arguments, the same speculations, right? So pretty much it doesn't matter what's the distance between the electrodes if capacitor is connected to the battery, assuming that the battery is healthy enough, is powerful enough, right? So of course it will be able to keep potential difference across the plates the same, 12 volts. Right? So it will be equal to delta V1 equals to delta V equals to, of course, 12 volts. Okay, great. So delta V is still the same. Then capacitance, will it be different now or the same?
Different.
Yeah, because capacitance is a property of geometry. It depends on the geometry. Geometry we changed. D1 now it's a D2. So capacitance must be different, right? Okay, so it's epsilon naught. Area, we don't change area of the plate, so it's still the same. That's why in the first place I didn't introduce any subscript next to area, right? So, and now, of course, this is divided by D2. Of course, you can plug numbers. You can do, again, manipulations, calculations. I hate doing those calculations, right? So I will keep, stay away from that till the very last moment, and you will see the reason why. Right, so instead of D1, I can use D1 over 2. D2, use D1 over 2. So factor of 2 goes upstairs, right, you see. Epsilon naught A over D1. What is this? Epsilon naught A over D1? Yeah, it's a capacitance over first situation. So it's a 2C1. Of course, you can just multiply this by a factor of 2, but still, I don't want to do that, even that. Okay, great. So now capacitance delta V we found, capacitance found. Now let's do the charge. And actually, I didn't write what needs to be found, actually. So we need to find charge in the second situation, essentially. Right. But as I said, we just wanted to analyze, essentially. We want to find all those three parameters for both situations. So Q2, of course, it will be C2 times delta V2. So C2, it's a 2C1. You see, I still refuse to do calculations. And delta V2, it's just delta V. Or I can write delta V1. Right. And what is that? C1 times delta V1. It's a Q1. Right, so from the previous part, that's why I kept refusing do the calculations, because I know I can recycle our numbers from the first part. You see, Q1's delta V1, it's our charge in the first case. So 2Q1. Okay, so now of course I cannot postpone anymore. Q1, it's this, so it will be of course 266 times 10 to the power of minus 10 coulombs. Right. So we double the charge, right, on the capacitor. So additional, so originally we had Q1, and then additional Q1 comes from where? What is the source? Huh?
Change in distance.
No. The source in change in distance cannot be the source. So originally we had Q1 amount of charge. And then once you reduce the spacing between the plates, now the charge is doubled to Q1. So of course the question, what is the source of electrons? It's not a voodoo. Nothing comes from out nowhere. Come on, the answer is obvious, right? So what we have a battery and we have a capacitor. If the amount of charge in the capacitor goes up at the expense of what? Battery. Charge just comes from the battery. There's only place, right? So yeah, just additional electrons comes from the battery, right? Then what happens if we, let's say, increase the spacing? Decrease. Where did the charge go in that case?
Battery.
Back to the battery. Basically, you will recharge the battery. You will sweat by changing the distance, and by doing this, you do work, and you will recharge the battery. So you can recharge the battery, discharge the battery, recharge, discharge. Okay, so it's a first situation. But you remember there was a second clicker question similar to this. So you remember, first we charged the battery when, we charged the capacitor when it was connected to the battery. Right? Then, you remember, we disconnected the battery after that, and started doing something with the spacing, the distance between the plates of the capacitor. Which parameter stayed the same in that case? Over here, potential difference stayed the same. Now, in that case, if we disconnect the battery, we charge the capacitor, disconnect the battery, and then we start changing the distance between the plates, which parameter stayed the same? Stays the same.
Relative to the battery?
Delta V, I would never be able to justify it. Let me put it this way. We had the discussion in the class, right? Do you remember discussion? Come on. You remember our discussions about the beautiful ocean liner in the Fort Lauderdale, right? So if you load, let's say, 1,000 people in that liner and make some assumptions that no one can swim well, and if that liner goes into the ocean, then if I ask you how many passengers are on the ship after 1 day of trip, 1,000, 2 days of trip, 1,000, because maybe they want to get out, but they cannot because they're trapped on the ship. So here the same. So once you charge this capacitor and disconnect the battery, it's like you first load 1,000 people on the boat and then send them into the ocean. So maybe they want to get out, but there's no way out because there was only one way out. It's a go back to the battery. But now, once you disconnect the battery, that 1,000 passengers will be there all the time. In this case, initial charge will be in the capacitor all the time. You can increase the spacing, reduce the spacing, throw them out, so they will be still there, right? So, but the potential difference, no, right? So in that case, charge stays the same. And again, this doesn't come from the formulas. You just need to analyze the situation carefully, right? So charge stays the same in that case. Then capacitance will be different because we changed the geometry. As a result, potential difference must also change in order to keep charge the same, constant, right? So it's a very similar situation, but now instead of potential difference staying the same, charge will stay the same, right? And very often students forget that, right? Okay, so that's why we reviewing this. Make sense? You remember our discussion, right? Great. Okay, so I think it should be enough. All right, now let me solve, maybe let me solve this problem and then couple of 3 conceptual questions, so 4 conceptual questions. Okay, this problem is quite straightforward. About Ohm's law, and usually students then don't have any troubles, of course, with Ohm's law and with most of this material. Right? So problem number 2. So what do we have? Physical situation. Somewhat can be very common. Let's say you work in the lab, right? So and you want to have some wire you found in the corner of the lab among some junk, right? The wire, and you want to know what's it made of, which material, which metal was used to make that wire. So what can you do? Of course, you can do some mechanical stuff, physical stuff, for example, measure the weight, right? So measure the volume, right? Then find the density. But since we are in electromagnetism course of electromagnetism, let's try to apply electromagnetic method. So essentially, you can take that piece of wire, you can measure the length, you can measure the diameter, then you can grab some battery, whatever available, apply it, measure the current, voltmeters, multimeters are everywhere, right? You can easily do it. So delta V, geometry of the resistor, right? So you should be able to calculate the resistance, and then you should be able to get, what do you need to know in order to find information about the material? Resistivity, no, not density. Density, it was mechanical approach. Here, we need to find resistivity. Find the resistivity, then open the reference book, and start looking for the material which matches your number. So essentially, let's solve the problem of this type. Right? And I think once I did something like this in the lab, right? But it wasn't a wire. I think it was some kind of rod, and I wanted to know what's the material. Right? So I did something similar. Okay. So let me write. So we have cylindrical wire. And let me write the parameters. So diameter, 2 millimeters. And let me emphasize, it's a diameter. And again, guys, be careful with the problem. Sometimes you give a diameter of some object and student treat it as the radius. Right? So just be careful because it's a very, very silly mistake. Right? Then length is, where is it? 46 meters. It's almost like a spool of wire, not just a wire. And then you apply, let me draw now this picture. So let's say this is my wire, length L, diameter, as I said, this, and it is connected to a battery. So let's say you found the battery of the potential difference 3.7 volts. Not very typical. Oh, power supply, whatever. So, and then you also measured the current. As I said, current is 2 amps. I think that's it, right? Oh, no, 2.5. I just looked at the different problems. Sorry, 2.5 amps. Yeah, 2.5 amps. 2 millimeters diameter. Yeah. Okay. So essentially, we just need to find the material. Find essentially resistivity, and then identify the material. Okay, so yeah, we need to find essentially resistivity. Okay, so essentially we discussed what needs to be done. So we just need to grab the formula for the resistance. That's where resistivity is, right? So R equals rho L over A, right? It's one way of finding a resistance. The second way resistance can be found, you just take the potential difference and divide it by the current which you measured, right? So now you just need to combine them in order to find the resistivity. Right. So from here, rho L over A equals to delta V over I. So now length is given, cross-sectional area, here we can easily find, right? So it's a circular cross-sectional area, and delta V and I is measured. So from here we can get rho equals to delta V times A divided by L times I times L. So delta V. And cross-sectional area, it's a pi d over 2 squared. Again, it's another place for mistakes whenever students try to calculate the cross-sectional area or area of the circle. Sometimes they just use pd squared. No, it's a pr squared or pd squared over 4. So I times L. Okay, so of course, diameter must be converted into meters, right? So must be in meters, let me emphasize. And that's it. Right. So of course, I'm not going to plug numbers, you can do it. So it will be 4 times 10 to the power of negative 7 ohms times meters. And actually, shame on me, I didn't look at the reference book to identify actually which material. But again, it's not the point. Right? So we just found resistance, and that's what we need. Right. Again, when I offer problems of similar to this, right? Again, 90% of students do great, right? So nothing fancy. So now a few conceptual questions. Let me write, so CQ. The first one, again, just to refresh, and that's what we do, just a review. What if I have this wire over some crazy shape? Let's say this is my wire. All right, and we apply potential difference. Of course, there will be some current. If I measure the current using, you remember how do we measure current? We take some cross-section perpendicular to the wire, right? And count amount of charge crossing that cross-section in some period of time. And then taking the ratio dq over dt gives us current. So every time you need to pick a cross-section. So what if I pick cross-section over here to measure current and over here to measure current? What can you say about those two currents? Are they going to be different, the same? Which one is larger or different?
Different.
Okay, Vlad. Huh? Okay, yeah, we're reviewing. I'm not asking you. Huh? You feel that something is fishy, right? So okay, you remember? Huh? Now you started thinking, right? Before you panic, and now you started thinking. You remember I told you when we discussed this, how to say, phenomena, I compared it with the property of water flowing through pipes of a different diameter. Water is almost impossible to compress. Okay, very difficult to compress, right? So if you have a pipe of a different diameter, let's say here diameter is this and then diameter is that. So of course, what happens over here? Water is flowing faster. And let's say you measure 5 liters per second crossing of 5 liters of water crossing, let's say this cross section in a second. Then if you look at the pipe with the larger diameter, now of course what does the water do? Flows slower, right? But because of the larger area, so the amount of water per unit time will be still exactly the same, 5 liters per second. So this analogy is exactly the same like what happens over here. So it doesn't matter what's the cross-sectional area. If there are no any junction points, current is going to be the same. It's conservation of current, right? Current is the same. So it doesn't matter where you are here or here, the same. And that's why whenever you have, you assemble the circuits, right? So plenty, right? So whenever you have, or if you have one loop circuit, only one loop, it doesn't matter where you are, at which part of the loop you will look, current will be the same. Sometimes it's just a thin wire, sometimes it can be something thicker, right? So current will be the same. If there are any junction, if there's no any junction point, right? So current stays the same. If there's a junction point, of course, you need to apply conservation of current in the presence of the junction point, right? Current is the same. Okay, good. So remember that. So I'm sure that first you panic and you answered. All right. But what about current density? If I ask you, what about current density over here and current density over there? Now it's definitely different because here's the current density. It's a current divided by the cross-sectional area. Currents are the same, but the cross-sectional areas are different. So obviously over here, current density is going to be larger, right? So than there, right? So current density is different, but currents are the same. So let me write. Let's say this is 1 and this is 2. So I1 equals to I2, but current density in the first will be larger than current density in the second section of the wire, right? Okay. Yeah, you forgot about this, right? Because in the class, I think like a few times, like 2 or 3 at least times, I poked because I noticed it takes a little bit of time in order to digest that, right? So it's common. So now, next conceptual question. So it's a first bullet. Now let me create this bullet. And what if I give you this situation? What if we have this resistor, right? And let's say we know that over here we have higher electric potential and here lower electric potential. Plus it means higher potential, there is lower potential. And let's say that the potential difference, okay, it's overlapping with the previous question, which is not good. So anyway, delta V equals to, what's the number? Oh yeah, 4 volts. So we know that side is at higher potential, this side is at lower potential, and the potential difference is 4 volts. Then let's say we also know the resistance. Which number? 2 ohms. So we can find current. Obviously, you can see the value of the current. So what will be the direction of that current? Don't overcomplicate things. What will be the direction of the current? So of course, first, what's the value of the current?
2.
Yeah, 4 divided by 2 will be 2, right? It's 2 amps of current. What's the direction? Left. Yeah, that way, right? So every time current flows from plus to minus, okay, from the region with higher electric potential to the region with lower electric potential. Then I can create situation more complicated. Maybe I create a junction point over here, and maybe there's another wire with the resistor with similar information. Then maybe there's another wire with the resistor and similar information. So you pretty much need to carefully get the directions of the currents and apply junction rule in order to find, for example, current in the wire number 4, right? Because I given a past question of this type, and there were lots of mass, with especially with the direction of the current. Whenever you see here plus minus, from plus to minus, right? So just be very careful, right? So, because even after this discussion, still there are plenty of mistakes. So current will be, of course, 4 volts over 2 amps. It will be 2 ohms. It will be 2 amps. And as you said, to the left. Good. And of course, as I said, I can create more difficult situation by combining several combination of this. Okay, now next. What if again, I will put a new bullet, so 1, 2, 3. What if I give you this part of the circuit? Let's say here I have one, what an ugly resistor. First resistor, then the second one, then this, and then this. So let's say we have this. Resistances R, and R. And let me call this point as point A and this point B. So what will be the equivalent resistance between points A and B? A few times in the past, I gave a question very similar to this. Right? So what will be the equivalent resistance between points A and B of this configuration of resistors? Okay, you the first time stop drawing. So what will be the equivalent resistance?
I see 2 in series.
2 in series, yes, 2 in series.
But it would just avoid the resistors, no? It would just avoid the resistors.
So that's, okay, I heard you. What do you think?
I was thinking the same thing.
The same thing? So what will be the number? Can you give me? 2, 3, 5, 276? A good number, I like it. All right, but my favorite is 5.
I think it's 0.
Agree? No? Yeah. Why? Okay, guys. For those if you don't see it immediately, you remember our discussion, right? So that how did I enter this classroom, right? So of course this question is stupid. Right? So now you recall, right? So of course I entered through the door because it's the least resistive option. I'm smart enough, okay, not maybe, in order to pick that option. I didn't try to get through the window, right, so hurting myself, or through the wall, killing myself, right? But again, those are also options. So smart enough, so of course I picked the least resistive option. Here, the same situation. When electrons come to this point, they have 3 options. Either hurting themselves really deeply, going through these 2 resistors, or hurting themselves getting through that resistor, or just going through the open door. Of course, they will go through the, in this case, it's an extreme, open door and having some resistance. Of course, all electrons, it means that all current will go this way, bypassing those 3 resistors completely. So those 3 resistors will do nothing over here. Right? Of course, it's absolutely stupid circuit. Right? No one would, of course, assemble anything like this. Right? But in order to sort of probe your understanding, so I create this. Okay, obviously, it's resistance will be 0, as you said. Right? But again, since still plenty of mistakes about the problems like this on the exam, so that's why I started adding this for discussion. So our equivalent is 0, right? Over here another. Then you remember after discussing something like this, and then on the exam I gave a different problem with the capacitors, and I still observed plenty of mistakes as a result. It's sort of like I'm getting some feedback, see the results, and then adjusting the exam review session, right? So in order to emphasize and push in the right places, right, of your brain, right? So what if I create this circuit? Don't look at this circuit from the practical point of view again. Like, this is absolutely stupid. So what if I have this? I have a battery, and then I have a bunch of capacitors. So the first one is here, then the second one is here, then the third one over there, and then let me connect them with this wire. So whatever, delta V or EMF, then let me label this C1, this C2, and this C3. And I actually want to discuss what can you say about, for example, charge in the capacitor C3. I just want to discuss that particular capacitor. Charge or maybe potential difference across capacitor C3. Any? You're still drawing. I think.
C3?
Yeah, that particular. I'm deeply in love with that capacitor.
What are you asking again?
Just some information about C3. Of course, we build this circuit, so we know the value of C3, whatever, it doesn't matter, C1, C2. And now I want to discuss maybe what can you say about the charge in this capacitor, or maybe potential difference across that particular capacitor. So just whatever, any information.
Would it be less than C1 and C2?
Okay, so you're saying less. You're also saying less than C3. Stare at that. Look at that. You don't know. Okay, so yeah, when I gave a problem like this on one of the exams and I saw students' responses, 50-50 almost, right? So I realized that I need to emphasize. Right. Any? I'm not asking for a number. Okay, guys. Look, this capacitor is connected to this wire, right? I mean, not this plate of the capacitor is connected to this wire, and this plate of the capacitor is connected to that wire. Those wires are connected. Right? So as a result, what can you say about, for example, potential difference across this? Of course it will be 0. We basically shorted it. So you see here, this point above the capacitor and this point below the capacitor, you see they belong to the same piece of wire. If we assume that capacitors are full, so current stop running, So pretty much electric potential at this top plate and the bottom plate, they're going to be the same. 5 volts, whatever, 3 volts minus 275 volts, it will be the same. So delta V across that capacitor will be 0. And if delta V is 0, it means what? What about the charge? It will be also 0. So that capacitor will be essentially doing there nothing, right? Again, it's like absolutely stupid circuit. But in order to discuss the physics and so that you would look at that. So yeah, of course, delta V across this will be 0 and the charge will be also 0. Right? It's sort of similar to this, this situation, right? So these resistors pretty much do nothing, and that capacitor also do nothing because we connected essentially the plates of the capacitor. So this will be, let me write it like this. So this will be 0 and this will be 0, right? Because potential is the same. See that now? Okay, good. Because again, once I give a problem like this, expecting that students would see immediately that there is a wire connecting, right? So, but actually it was like 50-50 response. Good? Now let's look at this circuit. Okay, now it's a problem. This will be number 3, and I need to start erasing. Okay, so number 3. So let me start with this diagram of this circuit. There will be 2 parts. No, essentially it's a. So let me trying to estimate the space. Then something similar below. They're connected. Then over here, let me put another resistor like this. And let's connect the whole thing to a battery. All right. Okay, so now let me give you some numbers. So EMF, electromotive force, basically potential difference over an ideal battery. So let's assume that this is an ideal battery. Right, so 6 volts. Of course, this is plus. Right, that is minus. Now let me label the resistors. So R1 10 ohms. Then these R2 also 10 ohms, and this is R3 5 ohms, and this R4 5 ohms, and this R5 7 ohms. Okay, and let me label this point, for example, point A, and this point B. So we need to find equivalent capacitance between points, resistance, equivalent resistance between points A and B. So again, everything is given. So we have the circuit is given. And so what do we need to find? In part A, equivalent resistance between points A and B. Basically this construction. So let's first start discussing, strictly speaking, which resistors are in series and which resistors are in parallel. Right. Any resistors which are connected either in series or in parallel. How about this, R1 and R2, are they in parallel? Then trust me. These, are they in parallel or not? No, right. Not, right. Okay, guys, do you remember what do we have to check in order to convince ourselves that resistors or whatever elements you have connected in parallel? What's the test? Potential difference. You need to look at the potential differences because sometimes elements can look parallel to each other graphically, but again, from the point of view of physics, we don't care about graphical, right? So we just need to check potential differences, the same or not. So strictly speaking, of course, this, for example, point on the left from resistor R1 and this point on the left from a resistor R2, they all belong to the same piece of metal. In this case, of course, there is no electrostatic equilibrium because we have dynamic situation, which is created by the battery. But in these situations, we assume that wires have a very, very small resistance. Essentially, we assume that there is no resistance, right, relative to resistances of the resistors, right? So pretty much it means that these and these points are all at the same electric potential, let's say 10 volts. But what about this point on the right of this resistor and this resistor? Between them, actually, there is this resistor, right? So strictly speaking, this resistor can give or can create a potential difference between this point and that point. As a result, strictly speaking, for now, we will dive deeper, of course. I understand what you're looking at. So strictly speaking, these resistors are not in parallel. The same story over here. They are not in parallel. Then this this resistor and this resistor, strictly speaking, are they in series? It looks like we have a junction point. At the junction point, current may change, right? So you see pretty much right now with this configuration, none of these resistors, they are not connected neither in series nor in parallel. So it sounds like we cannot apply the method of an equivalent resistance, right? But still, nevertheless, I ask for an equivalent resistance. Let me write that down. So it's an equivalent resistance. So now let's start looking deeper. Any thoughts? Again, I'm not asking you. any thoughts? Or maybe we can simplify this circuit.
Let's use symmetry.
It's like in your quiz, exactly. Yes. So now you need to start looking deeper, right? So it's a very common. There's sometimes on some Olympiads among physicists, they can give you gazillion different resistors, right, connected in very complicated configuration. But then once you start looking, using the symmetry or whatever ideas, you can, by removing a few resistors, that circuit becomes trivial, actually. So what's your idea about the symmetry? Maybe I can label more points. So we have this point A, this point B, and let's say this is point C, and this is point D. Let me just label all the points, actually all junction points, right, so which we have in this circuit. So any?
Would R5 not matter in this?
Can you justify it?
Like, it would be 0?
No, 0. What is 0? Because yeah, like when I graded this last quiz number 5, very often students just wrote that the resistance is 0. No, resistance is not 0. What is 0?
The current?
Okay, why?
Good question.
Yeah, it's an excellent question. You sure? You know, right? Okay, it feels like you look confident, right? So you know the answer? Okay, so let's analyze. So let's assume that over here, the electric potential is, I don't know, VA, right? And we want to find you know what, let me write over here. So this is electric potential A. And let's say, let me write the expression for the electric potential at point C, Vc. Of course, we need to take electric potential at point A. And, okay, probably you know it, before I started this, I should have discussed this situation. Look, what can you say about, for example, current flowing through this resistor and current flowing through that resistor? What can you say about these two currents? You said the magic word, symmetry. So for this current, it will experience exactly the same conditions, and this will experience exactly the same conditions, right? So as a result, this current and this current must be the same, must be the same. So now, let me go back to this. So we need to, in order to find electric potential at point C, we need to take electric potential at point A, which is on this side of the resistor. And then what happens when you go through this resistor? There will be voltage drop. So it will be minus current times resistor R1, which is 10 ohms, right? Now let's write something similar for the point D. And, okay, V at point D equals to, again, it's electric potential at point A minus the same current and resistance R2. But R1 and R2 are the same, right? So these are equal to each other. So as a result, what can you say about the electric potential at point C and the electric potential at point D? The same, right? So Vc equals to Vd. And as a result, you said something about zero. What is zero? Potential difference across the resistor. This resistor is zero. As a result, current, as you said, will be also zero, right? So delta V across CD will be zero. And of course, current through R5 will be also zero. So essentially, that resistor doesn't do anything in this circuit. It's exactly the same situation like in your quiz, take-home quiz, okay, number 5, except for here, geometry is different. Right, graphically different. Okay, so yeah, so it means that we can drop it, and the circuit will still work the same way. So now, once we drop that resistor, the rest of the circuit, how should we call it? Essentially trivial. After this, it will be trivial circuit. Of course, everyone, of course, see how this and this resistor, how these two resistors are connected. Of course, series. These two also in series, and then this in series is in parallel with these guys in series. Right? So now the rest is trivial. Right? Again, it's like your take-home quiz. Right? And so now R1 is in series with R3, and R2 is in series with R5. R4. 5 is out. Right. Okay, so let me just quickly finish it. R1, it will be R1. Okay, let me write R1 plus R3. So it will be 15 ohms, and the same for R24. 15 ohms, and then these are, of course, in parallel with each other. So R13 is in parallel with R24. So now, of course, we need to use those reciprocals. Right? So 1 over RAB, let me call it 1 over R13 plus 1 over R24. Very often I see in your solutions when you, instead of writing something like this, which is absolutely correct, you write something like this. I don't want to be really, really picky, right? So, but I understand what you mean. You're trying to combine simple, a reduced number of steps, but don't do it. Or sometimes it's like this, and then it is equal to RAB, something like this also, I see, right? So again, at the end, you will get the right answer, but so I will just write down the answer immediately. Right? Actually, these numbers are quite simple, so I don't have to, let me, 1 over 15 plus 1 over 15, it's a 2/15. And of course, from here, our equivalent will be 15 over 2. RAB will be 15 over 2 ohms. Okay, then it asks to find current taking from the battery, but of course it's trivial. So now also needs to find, let's find the current. So it's a part A, and now part B. Let's find the current. Not current here, not current there, just the current, total current taking from the battery. To simplify things. So it's just, of course, Ohm's law, EMF divided by the total resistance between points A and B. Right. 6 over 15 over 2 ohms. Numbers are not very nice. It's a 12/15, right? And that's current, of course, amps. So let me erase this. So the next problem is probably the most tedious, right? But straightforward. Once you get the idea, it's just a question of getting through simple mathematics, simple algebra. And you know what? Or maybe I should be able to fit it here. Yeah. So number 4. Is it clear? So it's analyze the circuit using the method of an equivalent resistance. We've done it, similar problems. And again, it's just a reviewing. So let me start with the circuit. Okay, let me write. So we need to analyze it. Again, these circuits will be in the middle, and I'm going to write on the left and the right sides instead of up and down. So I'm going to arrange it this way. And so first resistor, then the second resistor, then let's split. Right, so another one, then connect them and attach to the battery. So now let me give numbers. Battery delta V is 24 volts. Then R1 6 ohms. This R2 12 ohms. Then R3 4. And again, I created this problem many years ago. I don't know how I counted, but I miscounted, so now there's no resistor number 4. Now it's R5. R5, okay, let me write it better. 2 ohms. So analyzing it means that we need to find current through each of those resistors and potential differences across each of those resistances. Right, so let me write that. So we need to find I1, 2, 3, 5, no 4, and potential difference is delta V 1, 2, 3, and 5. Right. You remember this method, we just need to review it very quickly. Because very often I give problems like of this type. Before I would sometimes give a problem about the equivalent capacitance or equivalent resistance, and now since this was moved into the lab class, so now options are smaller. So I think we have everything. Yeah. So you remember the procedure. So first you need to simplify this circuit to the simplest possible, where you have just one equivalent resistor across the battery. Find something, and then you start moving back, finding what needs to be found. Right? So which resistors are in series or in parallel? R3 and 5 in series, and at the same time R1 and R2 are in parallel. Right? So, yeah. So let's do both of these steps at the same time. So these are in series, and these guys are in parallel. Right. Okay, so let me redraw this circuit immediately. So battery still works in the same way because that's how we developed the method. So we don't want to disturb the work of the rest of the circuit. Instead of R3 and 5, it will be R3, 5. And then instead of 1 and 2, R1, 2. Right. And delta V, still the same. Okay, let's just find these. So R3, 5, it will be R3 plus R5, 6. Then reciprocals. R1, 2 equals to 1 over R1 plus 1 over R2. Again, you can bring either to the common denominator and then flip it, or calculate it like this. It's up to you. I will just write down the answer immediately. So R1, 2 is 4 ohms. Number is actually quite nice. At least at the very beginning. And then later on, they will not be as nice. So first step. Now, of course, obviously, these two resistors in series. So these are in series. So we can simplify and redraw this circuit in the as simple as possible. So these across are equivalent, and battery still works in the same way. And of course, current taking from the battery is still the same. So 4 plus 6, it will be 10, right? So it's very, very nice numbers. So R equivalent will be R1, 2 plus R3, 5. So it will be 10 ohms. Right. Again, since we've done similar problems, so I'm not asking much. So, and now what we can find? We found equivalent resistance. We know the potential difference across the battery. So what can be found now?
We can find R equivalent.
No, we already found 10 ohms. This is the R equivalent. We already found it. So now, again, simple circuits, trivial questions. So we have potential difference across this resistor, which is 24 volts across 10 ohm resistor. So what can be found? Of course, current. Of course, trivial question. So yeah, now we can find the total current taking from the battery. So essentially, we're over here. We're finding this current I total, which is over here and over here. It's the same currents, because again, that's how this method was developed. Okay. So now we can find at least something. So I can write the total current taking from the battery. I don't want to write that. So delta V across the battery divided by R equivalent. So it will be 24 volts divided by 10 ohms, 2.4 amps. Okay. I wanted to say half of our problem done. No, it's not half. It's a 30% probably. And as I told you in the class, up to this point, 99% of students can do this easily, right? So, sometimes mistakes when instead of finding R equivalent, they used R 1 over R as an R equivalent. But again, that's really, really unnecessary mistakes. But then up to this point, maybe 40% can. No, here 99, here 90%, but the rest not high percentage, right? So can usually do. So now we have at least something, and now let's start moving back, finding what actually needs to be found. And now, of course, we need to use these pieces of physics, these pieces of information, what happens with the current and what happens with the potential differences across resistors connected in series or in parallel. Right? So first, in this guy inside, we have two resistors connected in series. So in series, which parameter stays the same? Is the same.
Potential difference.
Careful. So this resistor, equivalent resistor, is a resistor instead of these two guys connected in series. Current. Again, you can look at our slides, at our discussion, how we derived these formulas, and during the derivation, we also established these pieces of physics, right? So here, and again, usually these and these are given in the formula sheet. So in the series case, current is the same. Current in the equivalent resistor equals to the currents in the resistors connected in series, right? So just be careful. Again, in the past, maybe like 5 years ago, I didn't give these formulas, and of course students struggle more. So I decided, okay, I started giving this. Right. So you just look at the notes, not the notes, formula sheet. You should be able to identify. All right. So it means that I can write I12 equals to I35 and equals to our total current, which is the equivalent current through the equivalent resistor. And it is equal to 2.4 amps. So that's our, again, I usually call it as a bridge. And again, this current comes from there. Okay, so now once we have this bridge, now as a result, what can we find through these resistors? Okay, yeah, my question was not through across this, yeah, voltage, of course. Now currents, we know current through this, current through that. Now we should be able to find, and we found resistances R35, R12, so now we should be able to find potential differences. So delta V12, it will be Ohm's law, of course, it's a current times resistance. So R12 times I12, and of course the value of this current comes from the bridge. We're just getting all the information from the bridge. And this comes from here. Let me circle it. So R12. So it's 4 ohms times 2.4 amps and 9.6 volts potential difference rate. 9.6 volts. Of course, now potential difference across R35 you can find using two options. Either 24 minus that, but I still prefer to use the Ohm's law. But again, it's up to you, right? So delta V35, it will be equals to R35 times I35. And again, this current comes from the bridge. Right. So you can plug and you will get 14.4 volts. Right? Yeah. So the first step didn't give us any of the information which we need to find. Okay, so what a big deal. Next in the next step, we will find everything. So now we exhausted the bridge. Nothing else can be obtained from here. So now we need to make the next step from here to there. But now in one step, there will be two steps. Inside of this, there are two in parallel. Inside of this, there are two in series. So let's just first, which one? OK, let's discuss in parallel. So delta V to 1 equals to delta V2 equals to delta V. OK, so actually, Vlad, now since we are dealing with in parallel case, so now it's a potential differences, right? So potential differences with the parallel case. And it is equal to delta V 1, 2. And of course, delta V 1, 2 we found over here. Oh, here. So let me use green color. You see everything is linked, everything is connected. So previous steps need to be used in the next step. So that is 9.6 volts. So that's our next bridge. And so now we should be able to find two parameters. Actually, we already found delta V1 and delta V2, which are our unknowns, right? So now we should be able to find currents through the first and the second resistor, because resistances are given, potential differences we found. So I1 equals to delta V1 divided by R1. All right, so 9.6 divided by R1 is 6. It's 1.6, right? 1.6 amps, right? Yeah. And so I2 delta V2 divided by R2. Okay. 9.6. Again, it comes from the bridge, and this also comes from the bridge. Divided by R2 12. Okay, no way. I will look at my notes. So it's a 0.8 amps. Wait, amps. So we finished analyzing resistor R1 and R2. Potential differences are in the bridge. Currents we found from the bridge. But we still have inside of R35 two resistors connected in series. So now let's just final push. So in series, which parameter is the same? Current. So it's I3 equals to I5 equals to I35, and I35 is here from this. Wait, that's delta V. Sorry. Wrong address. I have to be careful. All right, so wrong address. So current I35, it's here in the bridge. Right. It happens. All right, so this. Right. So that's 2.4 amps. Right. And so now again, Ohm's law needs to be applied twice. So delta V3, I3 times R3. And again, R3 comes from the bridge. So you can plug. Current is 2.4 amps. Resistance is 4 ohms. So it will be 9.6 volts. Right? Yeah. And similar. Delta V5, I5 times R5. And again, I5 comes from that bridge. Okay, what's the number? 4.8 volts. Again, somewhat tedious, especially when you have 4 resistors. If it's 3, okay, it's faster. But again, once you just need to go through this algebra, right? And again, a little bit tedious, but again, straightforward. And again, I'm a big fan of this because it's so well structured, so well connected, right? So pretty much you don't have to think, you just need to roll like down the hill. Right? And you will end up with the right place if you, of course, are following the procedure. Good? Mm-hmm. Mm-hmm. Because very often in this second part of the problem, very often students just assume that this delta V across all those resistors and start writing nonsense, right? So, you know what? I just realized. You know what? No, I don't want to write. Pretty much now I want to move to the Kirchhoff rules. What's left? Kirchhoff rules, because we discussed this, discussed that. And then the last couple of problems, one problem in conceptual questions will be about electric power. So what I realized, I didn't write those mnemonic rules which we developed for the loop rule. But I think you remember, right? So, okay, we will practice. So essentially, or maybe let me write them down. And that will be like a review also. So, if we have a battery, so let's say like this, so it's a plus and minus, and you remember every time when you analyze when you apply loop rule, you need to pick a travel direction. So let's assume that in this case, travel direction is this way. Travel. So if you travel from minus to plus, electric potential goes up. And if the battery, EMF of the battery is given, so potential difference, delta V contribution to this loop equation will be plus EMF. So it's a rule number 1. Rule number 2, again, about the battery. So let's say I keep the same battery, so it's a plus minus. But now I will flip the direction, travel direction. So now let's say we travel this way across the battery. So in this case, if you travel from plus to minus, electric potential drops, so it will be negative potential difference, right? So contribution to this delta V will be minus EMF. Delta V equals to minus EMF. So then rule number 3, now about resistors. So let's assume that we have this resistor, R. Usually you build the circuit, you know resistances. Then let's assume that travel direction you pick this way. And what else do we usually assume? Current direction. Again, every time it's just a pure guess. Don't think too much. Okay, let's assume that I picked this direction as our current direction, I. So now, mnemonic rule. If both directions are the same, contribution is positive or negative, do you remember? Negative, minus IR. Right? Current is unknown, resistance usually given, most of the time, right, in the classical problems. So delta V is minus I times R. Okay, and the last rule, so again, this is our resistor. There is some overlapping between these pictures, which is not good, but okay. So let's assume that travel is, okay, that's ugly travel. Then current direction, let's assume, is opposite. So this is current. So now if directions are opposite, the contribution is positive, plus IR. These rules I don't feel like giving on the formula sheet, right? So you either remember or just quickly restore it somewhere on the back page. Right. So that's it. And now let's just pick one of the problems and quickly write them down. Yeah, let me start erasing this. So that will be number 5. Oh, it's loose now. You remember when we discussed these problems, I told you that it's up to you which direction to pick as a travel direction, which direction to pick as a current direction. It's basically like universal freedom, right? Constitutional freedom. But the thing is, I don't give that freedom on the exam. And the reason is quite practical, pragmatic. I remember when I first started teaching this course, and I remember a graduate student worked with me as a TA, right? And I didn't give any directions, so I give the exam. So then I collected the exam papers, and I assigned my TA to grade these problems, right? Multi-loop problem. So he grabbed all the envelopes, went to his cubicle in the second floor, and then in half an hour he came back saying, "Kill me." You understand why? Every student picked her own directions. And now this poor guy had to sit and compare for each element. There were like 15 elements in the whole circuit, right? And for 350 students, right? So it was really nasty from my side. So after that point, I realized, oh my God, no. You need to understand that you have a freedom, but I'm not giving you that freedom. So pretty much now, every time if I give a problem of this time, directions will be given. And I'm asking, don't change those directions. Again, we will check to make sure that if you change directions, everything is correct. But it's just from the practical point of view. Otherwise, grading is essentially killer, right? So, of course, when I finished grading my problem, of course, I went and helped him to grade that particular problem. Right? Because, yeah, I didn't realize when I was creating the exam. Experience. So 4, 5. So let me draw the circuit. Just trying to estimate the amount of space so that the picture would be nice. So the battery, then a resistor, then another resistor on the way down, then another battery, then over here let me put some resistor. Okay, so first, now another loop. Three batteries and tons of resistors. Okay, something like this. I think I didn't miss anything. So now let me label. And most of the time I even don't give numbers, just write it in symbols, just in equations. Right? In this case, there are numbers. So EMF 1. You know what? No, I will write numbers separately. I will just use the symbols on this circuit. EMF 1, then this will be R1, then R2. This is EMF 2, EMF 3, R3, R4, and this will be 5. Yeah. Okay, now let me give you numbers. Okay, let me step away this. So the first battery is 3 volts. Basically, after this, there will be another big problem, and then conceptual question, and we will cover today. This exam, significantly less, okay, not significantly less amount of material for the second midterm exam than for the first or the second. The last one, the final exam. All right. EMF 2 equals to EMF 3 equals to 6 volts. And then the resistances R1, 2, 3, 4, they're all the same, 2 ohms. And R5, Yeah, that's 4. Whew, enough. So, and the question, of course, analyze this circuit. Analyze the circuit full of resistors. Essentially, again, that circuit trinity, 3 parameters, R, I, delta V. R's are given, so we need to find currents. And then once you know the currents, of course, finding voltage drops across each resistor is banal, Ohm's law, just Ri, right? So pretty much, essentially, we just need to find currents. Okay, all right. So again, I will start with first 3 preliminary steps. You don't have to write that about 3 preliminary steps. Just actually, all the directions will be given. So you don't need to do anything. You just need to write down equations. Start writing down the equations. But in this case, of course, I need to go through the preliminary steps. So this junction point, let me call A, B. Then, what can you say about the current between points A and B in this part of the circuit, and you're still drawing? What can you say about the current in this part of the circuit between points A and B? No. Don't guess. You're guessing, right? So just 0. No, in simple. Look, you remember we discussed conservation of current, that it doesn't matter what's the cross-sectional area, current will be the same since there are no any junction points. So now I'm asking you, look, what can you say about the current between this junction point and these junction points over here? There are no any junction points. As a result, what can you say about the current? The same constant, of course, right? The question is trivial. There's no point for panicking. And right, current is the same. So, of course, we don't know. It's our unknown, but we can say for sure current must be the same. So let's just introduce it as the first unknown. Direction, pure guess. I will just look at my notes so that I would follow my notes. I picked this direction, but again, it's a pure guess. I have no idea what will be the actual direction. Because essentially what happens, look here, we have 3 batteries fighting with each other, with their own currents. This battery is trying to drive current from plus to minus through this loop, through that loop. Then this battery is trying to do the same, from plus to minus, trying to drive through this loop and that loop. Then this battery through this loop and that loop. So we have like tons of current fighting with each other in each loop. So who knows which current is going to win unless you solve the system of equations. So that's why we're guessing. And then at the end, if current is positive, great, you guess the direction correctly. If current is negative, bigger deal, right? So just make a statement that the actual direction is opposite. Okay, so I1, then I2, I think in this, in this in this part of the circuit between A and B, and I guess the direction down. I2 is down. That's my second current. And of course, in this part of the circuit, there will be current I3. Which direction? Again, counterclockwise. I3. And again, remember, they only up to points A and B. Right? Because at junction points, currents merge, current gets split. Right? And the last step which we need to introduce before we start writing down the equations, travel directions, right? So travel directions, again, it's up to you which directions to use. In this case, I picked what? Counterclockwise. I don't know why I used counterclockwise. So loop 1, travel. And I think the same here. So it's a loop 2, that's the travel direction. So now all the preliminary steps are done, so now we can start writing down the equations. Right, so yeah. So first, junction rule. So junction rule, the total amount of current entering must be equal, entering junction points must be equal to the total amount of current leaving. For junction point A, can you give me immediately the equation? Okay, maybe I can write, so sum of all currents in must be equal to the total amount of currents leaving junction point A. This is junction point A. It's trivial, right? So what's the equation? So which currents entering in on this side?
For A?
Yeah, for A, for example. Yeah, just I3, only one current enters the junction point. And leaving junction point, yeah, it's absolutely trivial situation, right? Again, I noticed the biggest mistake with this equation that students are so focusing on the loop rule that sometimes they just forget to apply the junction rule. And when they see the grading, oh damn it, how could I forget that to apply that equation? And it's trivial. Again, of course, for junction rule, for junction point B, the equation will be
The opposite.
okay, essentially the same.
Oh.
You just need to, it will be just I1 plus I2 on this side and I3 will be on that side. Essentially it's the same, so skip it. Right? Again, you can write it down, but at least make a statement that it's not needed, it's redundant, essentially linearly dependent on this. So essentially, and I want from you only equations which we need to solve the problem. So if you don't feel like writing equation for junction point B, okay, I understand that, and it's understandable. All right. So we still need to get two equations because overall we have three unknowns. Actually, let me write that down. So we need to find essentially I1, I2, and I3. Three currents. Three unknowns, there must be three algebraic equations in this case. One is we have, so now we need two. We need to write two equations. Loop 1 and loop 2. So now loop rule. Right. So loop 1. And of course, again, as I said in the class, be careful with the subscript. Make sure that, because even sometimes when I write on the whiteboard, I can make a mistake like over there. Instead of I wrote R. Okay, loop 1, you remember my minor compulsion. I usually like to start in front just before the battery. Again, don't ask me why. I like it. So loop this way, so I will start here. So first we cross the battery. So what's the contribution to the loop equation from the battery? So we're traveling this way. So this is plus, this is minus. So we're traveling from plus to minus. You see travel. Over here, when you analyze the battery, you need to remember, we need to know only travel direction. It doesn't care about current direction. It's a mistake. I remember like several years ago, I had a very strong student, right, and she got confused at this particular place, right, at the point. So travel direction we need to know to analyze the battery. So as a result, contribution? Negative minus EMF 1 subscripts. Of course, guys, be careful with the subscripts. Minus, it's rule number 2, this. So it's a minus EMF 1. Okay, I don't like to start the equation with a negative value. So then after this, we need to go across this resistor. What's the contribution to the loop equation when we cross this resistor? You see first the battery, now resistor. So the rules are here, there. Directions. Are they the same or opposite? You see the mnemonic rule. Directions are the same. Travel counterclockwise. So direction, travel direction this way. Current I1 also the same way. So directions are the same. So contribution must be negative, right? Minus I1 R4. Minus I1 R4. Great. So now we're done with this resistor. Now we need to go across the battery. And so what will be the contribution when we move across battery epsilon 2?
Minus epsilon 2? Would they cancel out?
No, well, canceling, who knows? The equation will take care of that cancellation or not cancellation, right? We just want to write the... That's the beauty of theoretical physics very often. You just, if you apply the laws correctly, right, so you can you guarantee that the answer will be correct, right? So, and everything will be shown automatically. Cancellation or not cancellation, acceleration or deceleration, everything will pop up. That's the beauty of fundamental theoretical equations, right? So we're traveling from minus to plus. You see, loop direction. We're still in this loop number 1, so we're moving into counterclockwise direction. So across this battery, we're moving up. So from minus to plus. So as a result, contribution is plus. From minus to plus, contribution is positive. Electric potential increases across the battery. Right? So plus EMF 2. I should have started in front of battery 2, then I will have positive value, positive number at the beginning of the equation. Great. So now this resistor R5. What will be the contribution?
Yeah,
I'm moving away from the rules.
yeah, it's positive I2 R5.
R2, I2 R5. Yeah, positive. Again, so now the current is this current, I2, because again, that's another common place for mistakes, typical place for mistakes. Sometimes students still using current I1, but now it's a current I2. So current is down, travel direction is up. Directions are opposite. You see? Loop direction up when we move across this resistor, but the current I2 is down. Opposite directions. It's in this case rule number 4. Contribution is positive. So it's a plus I2 R5. Plus I2 R5. Whew. So done with this small bridge. Now we need to cross this resistor R1. So what will be the contribution? Resistor R1 if we move, or when we move across the resistor R1. Okay, good. You picked the correct current. So negative travel direction this way, current direction also the same way. So directions are the same. Contribution must be negative. Minus I1 R1. Yeah. Minus I1 and R1. Okay. So and now after this we're back to the starting point, and now the next it's like lots of mistakes. You need to complete the equation. You need to write it as an equation. Again, we keep saying we're not philosophers or psychologists. We need to follow the language of mathematics, right? So must be equal 0. If you don't write 0, immediately at least a couple of points will be subtracted. Right? Because very often, yes, students just concentrate on these correct signs and correct currents, and at the end they just, who cares about that 0, right? Okay, equation number 2. So now this final equation, loop 2. Where should I start? I would probably start here. Let me check. Yeah, that's my starting point. So that's my starting point. And so first I move across epsilon 3, right? And plus, yeah, from minus to plus, so contribution is positive, plus EMF 3. Okay, I will write the rest of the rest of the terms myself, right? So it looks like you're comfortable with this. So then this resistor current that way, travel that way, so directions are the same, must be contribution is negative. So it's a minus I3 R2. Minus I3 R2. Then next, now this resistor travel down, current also down, both directions. You see, travel direction is down, current I2 is also down. Directions are the same, so contribution is negative. So it's a minus I2 R5. Right. Then this battery. Okay, so now we move across this battery. So what will be the contribution? Yeah, good. So now we travel from plus to minus. Contribution is from plus to minus. Contribution is negative, minus EMF 2. Right. Okay, and after this, we're going across this resistor. Travel up, current up, directions the same. Contribution is negative, so it's a minus I3 R3. Okay, and again, it must be equal to 0. Equation number 3. So now 3 equations, 3 unknowns, physics is over. So nothing else. So we applied all the physical ideas, physical concept. The rest is just mathematics, just simple algebra. Of course, if I ask you to solve this system, I wouldn't even guarantee that I would be able to get through all this without making some silly mistakes, right? Because it's very tedious. Of course, now softwares can calculate this in no time. You just enter the proper coefficients, and it will give you the answer in a second, right? So that's why I stopped asking for the solution, because you would spend like, I don't know, 1/3 of the exam solving this system. Okay, in this particular case, right? So I can write the rest is algebra. Actually, it's just the algebra, not even calculus. Wait. A simple system of algebraic equations. The rest is algebra. So in this particular example, I1 equals to 0.5 amps. So what can we say about the current I1? Direction of the current I1. You see the value?
Yeah.
So it means that the current direction. Yeah, it's correct. So we picked the correct direction for the current I1. Guessed. Right? So then I2 is minus 0.25 amps. So in this case, what can we say about direction of current I2? We're bad at guessing, right? So in this case, current I2 is actually up, must flow up, right? So I2 is actually upward, right? So basically because of this minus. And I3 is 0.25 amps. Okay, I3 again we just guessed direction correctly. So I3 direction is correct. Again, directions are given, so writing down this equation should take you 5 minutes, right? So top, right? So just be careful with subscripts. And again, don't forget about this, because I was quite every time surprised. Forget to write the easiest equation. Any questions? Again, I usually don't ask for the numerical calculations, so it will be number 6. Now, the last big problem, and then one additional conceptual question, and that's it. So it's almost 2 hours. So that will be about electric power, the last section which we discussed like a couple of classes ago, before we started moving into the magnetism. So what is given? Let's say we have a flashlight bulb. Which is rated with these numbers. So rated at 2 watts. Rated at B. Okay, I will write B subscript. B stands for bulb. What did I say? 2 watts. And of course, when it says rated, which additional piece of information must be given? Yeah, potential difference. So you need to apply a certain potential difference in order to get this wattage. So let me write when delta V across the bulb, again, B stands for bulb, is 3 volts. Okay, information about the bulb. We have this particular bulb. If you apply 3 volts, you can get 2 watts of power. But we don't have this 3-volt battery. We have only 9 volts battery. EMF, but we have EMF equals to 9-volt battery. So of course, if we apply 9 volts battery to that across that bulb, of course, this wattage would be wrong. So pretty much now, what if we try to add additional resistor in series with the bulb? So we will get exactly this potential difference across the bulb and this wattage across the bulb. So now we just want to add additional resistor to get the rated values. Okay, so we want to add a resistor, which we want to find the value, R question mark. We want to add a resistor in series so that we can get that rated value. Right, and of course potential difference. Right. So we want to operate the bulb sort of at the required conditions. Okay, so let me draw the circuit. So this will be the resistor, value of which we want to find. Then there will be bulb. Again, I told you how I drew the bulbs. I drew the bulb. For me, it's easier than that circuit symbol. And our battery, which is 9 volt. So that's our circuit, so EMF. So what else? What else? Power I gave, potential difference there. And we need to find, maybe I should write separately here. So we need to find, again, emphasize, resistance of that bulb. Of the resistor, sorry, of the resistor. Okay, so now, okay, let you finish it. So let's just show on the circuit our goal, our desire. So essentially, what do we want to get across this bulb? Eventually, if we pick the correct resistor, what will be the voltage drop across the bulb? If we pick the correct resistor, so pretty much we're trying to imagine the correct situation.
3 volts.
3 volts. That's our desire. That's what we want. So delta V across the battery, 3 volts. That's what we want to achieve. Of course, over here, the voltage drop will be some delta V R, which we don't know. Just writing it. But there, that we know. Then, what can you say about the current through the bulb? Or you know what? Let me ask. You knew that I will start bugging you again. Okay. So what can you say about the current through the resistor and through the bulb? Currents through the resistor and through the bulb. Anything specific? It's one loop only. The same. Ah, okay, I didn't hear it. So the same, of course, the same, right? So current over here and current over there, the same. Great. So now, what else? What else? I think for the picture, it should be enough, right? So now, can we find that value of the current? This value of the current, which is the same, from our from our desires. We want to get a certain situation. We want to create a certain situation in terms of for the bulb. So can we get the current? Yeah, so we have information about the bulb power, right? So this is given. And then what else is given? Potential difference. So potential difference is given. So from this formula, we should be able to get the current, which we want to get through the bulb, right? Which will flow through the bulb if we want to satisfy those conditions, right? So, great. We can get current through the bulb. Right. So. First, let me write the formula in general. So P, it's a delta V times I. And of course, in this case, I will put the subscripts B and B. Next to the current, I will drop subscript B because it will be the same for both bulb and the resistor, right? Makes sense. So let's get current. So of course, from here, current will be equals to the power divided by the potential difference across the bulb. Okay, so of course you can plug numbers. I'm not going to do it. Right. Actually, yeah, we can do it. But I will still keep writing this. Power is 2 divided by 3, so 2/3 amps. So that should be the current if we want to satisfy these conditions. Great, so now next step. What else can be done? We just found the current. Current is given. Not given, found. We found the current, right? So, again, it's essentially a circuit full of resistors. Circuit trinity Ri delta V. Resistance is, okay, this is, we want to find. Current, we just discussed. Current will be the same. So what's the last parameter which can be analyzed? Potential difference. So now we need to discuss what is the story with the potential difference, right? So potential difference is in our loop rule, right? So let's just apply loop rule. Right? So now, next step, in order to discuss potential differences, let's just apply loop rule. Okay, in order to apply loop rule, current direction we know, we don't have to guess. Let's just pick a travel direction in order to follow the steps correctly. So let me pick, this is my travel direction. Right. And so now let's start applying these rules. So sum of all potential differences must be equal to 0. So first we travel across the battery from minus to plus. Of course, contribution is positive, right? So plus EMF. Then there will be current direction this way, travel direction also that way. Contribution must be negative, minus IR. Of course, I'm sure that if I give you a problem like this on the exam, of course, you wouldn't apply loop rule. You will just immediately say, this plus this potential difference must be equal to the EMF, right? But I just wanted to connect to what we just discussed, right? All right, so will be minus I times R, which is not known, R. And there will be, of course, voltage drop of 3 volts. All right, and again, it will be minus. So again, travel direction this way, current that way. So through the resistor, of course, it will be negative contribution. So, but in this case, it's not just IR, we know the potential voltage drop which we want to get. So it will be minus delta VB. Minus delta VB. And we're back to the starting point, so it's 0. So how many unknowns in this equation which we wrote? This is given. Current we found. Resistance we want to find, and this is given. So problem essentially solved, right? So now we just need to solve it for R. Yeah, that's our R. So this term I will move to that side. So it will be IR equals to EMF minus delta VB. And now resistance will be that divided by resistance will be EMF minus delta V divided by current. In current we have, and I will still write in terms of these symbols current, right, in order to have sort of like a general formula at the end. So since current downstairs, so essentially we need to flip this. So delta V will be in the denominator, in the numerator, and P will be in the denominator, right? So if you plug it, so it will be delta VB divided by P and EMF minus potential difference across the battery. So basically, we need to plug over here that I, it's a P over delta V, B plugging. Okay, so if you plug numbers, which I will probably skip, or maybe. So 3 volts divided by 2 watts and 9 volts minus 3 volts. Yeah. 6. It will be 9 ohms, 9 ohm resistor, right? 9 ohm resistor. So the 6, 3 times 3, 9. 9 ohm resistor. So you need to connect in series 9 ohm resistor in order to drive this bulb properly. Because who knows, if you apply 9 volts directly, maybe you can just burn it, right? So damage the bulb, who knows. I think this problem was given once on the one of the exams, right? Something similar. But of course, for the exam, it was a little bit of a stretch. Although once we discuss this, it shouldn't be that challenging. You know, yeah, the final conceptual questions. Good? Mm-hmm. And then we can call it a day. And I can go continue preparing the exam, the actual exam. Let's call it 7, although it's conceptual. Oh, something like this. So what if we have, okay, CQ. We have a battery, then there is a bulb, then there is another bulb, and let's connect them like this, and then there is a switch over here, right? Switch S. Yeah, let's say EMF. Let's say resistance of this bulb is RA, and this is B, resistance RB, no numbers. So in part A, what if S is open? Let's just estimate the power in, okay, basically light produced by this and that bulb, assuming that there's no heating losses, so everything goes into the light. Right. So let's first find the current, the total current. What will be the total current flowing through these bulbs? And of course, that current will be the same for both bulbs, right? Yeah, yeah. So of course, the total current will be EMF divided by RA plus RB. And of course, then we can write down expression for the power. Let's say power of bulb A. Which formula is better to use in order to... Which one? VI. No, I wouldn't say that VI will be better because we don't have information about the voltage drop over here and voltage drop over there. Of course, although... No, they're not the same. That's why on purpose, right? So I would say it will be better write I squared times R, since we have information about I and R, let's assume given. So I think it will be slightly better. Again, any formulas out of those three can be used. Right? So it will be I squared times RA. So it will be currents are the same. And then P through the bulb B will be I squared times RB. So pretty much which power is going to generate more light, it depends on the resistance. The bulb with the larger resistance is going to generate, produce more light. Right? So for example, I write, so if RA is larger than RB, then a power through the bulb A will be larger than the power produced by the bulb B. Right? Just simple analysis. Okay, now part B. What if S is closed? You know that I'm going to ask you. I move closer, waiting for you. So what can you say, for example, if we close the switch S, what can you say about the power produced by the bulb B? And what happens to the power produced by the bulb A? Not very confident. Okay. It's an answer for A, right? Sorry. No. Huh? So what can you say about the power produced by the bulb B? Mm-hmm. I'm just trying to give you the easier choice. Lower. How lower? What do you think? Zero. You saw? Oh. Any sparks? Stroke of genius, or what is it? Okay, you remember over there we discussed today at least, at least once, maybe more, I don't remember. When we tried to find the equivalent resistance of those, you remember, like 3 or 2 resistors, and there was a wire going across. So what was the equivalent resistance? 0, right? So now it's sort of similar here we have. Look, now we close this switch. Okay, let me use different color. So what will be the current flowing through this resistor?
Would it be 0?
You're guessing? I don't feel the confidence. You remember our discussion. Let's say electron over here traveling to this junction point, making a decision. Should it go this way or should it go this way? It's like the same discussion. How should I enter this room? Through the door or through the window? Again, it's also possible, but of course I'm smart enough in order to pick the easiest solution, right? So of course, instead of getting through this resistor, struggling or hurting myself, of course I can go through the open door, right? So of course, all electrons, all current will just go this way. Here current will be what? 0, right? So here current will be 0 in part B, and all current will flow through the bulb A only. So now as a result, so what will happen to the power through the bulb A relative to the first case? It will go up. So now more current will be flowing through this, because now total current will be just EMF divided by RA, right? So current will be larger. Of course, power of the bulb A will be larger, and power through the bulb B will be, it will be absolutely dark, right? So, right. Okay. So basically, with this, when we close the switch, we'll just short this bulb, right? So we just bypass it. So this bulb will be absolutely useless right over there. Okay. I think it should be enough. Here, there's another problem, but essentially it's about this formula applied. Just a pure mathematics, nothing else. I think it should be enough. Again, in terms of material, now it's the exam with the smallest amount of material, right? Because now RC circuits kind of in the lab, right? And you just discussed it only this week, so I don't feel confident giving it to you in this exam. Usually, here there will be also a big chunk of the material about RC circuits with about all those functions. Okay, so if you have any questions, you can ask now or during the weekend. All right, you can send me an email, and I should be able to answer.